Okay, so this is the line we finished with yesterday. Um, there is another version of this equation, and that is rearranged in what is called general form, where all the variables appear on one side. So I'm going to rearrange this. Let's move the x from right to left. And then it's not a requirement, but I think it's nicer if everything is an integer in this. So I'm going to multiply by a common denominator, which in this case is just 7. And this is referred to as the general form of a line, or sometimes called a general linear equation. This is most commonly seen when we do simultaneous equations. Working with more than one line at a time, we find out where they intersect, if they intersect, all that sort of fun. Two equations, two variables. We tend to write them in this general form. This also makes it, in my opinion, slightly easier to actually draw the line. But I have technology. If I'm drawing my line, I'm probably doing it on my computer, on my calculator. If I'm using the calculator, I must, in order to graph a line, have it in slope-intercept form, because every equation I want to graph must be entered in the calculator in the form y equals. So if I want to graph something, I've got to have it written this way on this device. It is possible to draw graphs directly in your MacBook. This little symbol down here for the MacBook grapher can write in any of the forms of a line, no matter what equation we write it in, whether it's general form, slope, intercept, or even point slope, it'll create the appropriate graph. If you don't have yours pinned to the taskbar, you can find it by going to the Launchpad and going to Other. There's our grapher there. But there are dozens of other graphing applications, Desmos, Wolfram Alpha, Mathematica, etc., that are available when we're not sitting in class, at which point I'm going to be using this. Now, if I want to put this line in here, I have to make a decision. And that's what syntax do I use to type that in. I see this number as number times x. And if I write that, -5/7x, like that, that's how the calculator sees it too, because it multiplies and divides from left to right. This makes me twitchy because it looks like it should be 5/7x, and that's not how it should be written. So instead of doing that, I tend to normally put the x on top by default in any fraction. That's basically combining these two terms on the top. Not a requirement, but I think it helps. You could also put the number in parentheses to write it that way. It's your call. Plus 11/7. There's my line. We should have the intercept that's 11/7, right? So if I hit the trace button, it defaults to x being 0. That's the center of this window, left to right. This, by the way, is under Zoom standard, option number 6. It goes from -10 to 10 and -10 to 10. If I hit trace, here's the problem. It gives me a decimal. Is that 11/7? I don't know. Yes, yes, it is. But I wouldn't have recognized that necessarily from here. So having a visual is good, but it's not always helpful. There is another intercept on this graph. But it's not the y-axis, it's the x-axis. How do I find that? Exactly. Now, I can't plug in with the trace to put in y equals 0, but I can ask the calculator above the trace button, it says calc. I can ask the calculator to calculate for me, and one of the things it will calculate is where our graph is 0. But it doesn't do it directly. It does it by wiggling back and forth, looking for changes between positive and negative. It's a result we'll get to later as to why that works. So it's going to ask me, well, where's a little bit to the left of where you think this is 0? I think it's between here and here. Notice it puts a little flag up. This is your left edge. And now it asks me for a right edge. I use the arrow keys and I move over until I'm sure I'm to the right of it, which I know I'm at because these numbers are now negative. I've gone from above to below. And then it asks me for a guess. I can be anywhere between those two. I can just stay right here and hit enter again, and then it finds it. And 2.2, if I set y equal to 0, actually, let me do it in this version. If I set y equal to 0, I get x is 11 over 5, and that's 2.2. We found the right number. In general, to draw a line, I need 2 points. The intercepts are the easiest ones to find. X is 0 gives me the y-intercept. Y is 0 gives me the x-intercept. Questions? I mentioned in passing earlier that we have places where we use more than one line. Simultaneous equations shows up less frequently in this course, but it does show up. But more often I'm comparing lines. So if I've got two lines, I can compare them to each other. What's it mean for two lines to be parallel? They never intersect. So I have line 1. I want another line that doesn't cross this. Well, this line has a slope. What do you know about the new line that I want to draw that doesn't cross? Because otherwise, it'll either be a little bit steeper, and then they'd cross back here, or it'd be a little bit shallower, and they'd cross over to the... So depending on which, they have to have the same slope, and then they'll never cross. Line 1 is parallel to line 2 if the slope of line 1 is the same as the slope of line 2. However, this does lead me to a problem. If my line is vertical, what's its slope? Undefined. A horizontal line has a slope of 0. If my line is vertical, it doesn't have a slope. How can I do this? So there needs to be a caveat here that says if the slopes are equal or they're both vertical. I mentioned yesterday that Euclid assumed the universe was flat. All of Euclidean geometry, all of these ideas are based on the idea that we are working on a flat surface, top of the table in front of you. A local environment on the Earth works like this, but the entire space is curved. If I think of the surface of the Earth, like we talked about going from Moscow, I don't remember where we were going, but Moscow to New York or something like that. You have to go through the Earth to draw a straight line. If we work on the surface of a ball, then we have to change the way we define these things. There's an entire field of study called non-Euclidean geometry that changes the ground rules. I'll save that for that course, SMA210. We won't do it here. I wanted you to know there's some other weird things here. Depending on the way I give you the line, general form, as opposed to slope-intercept form, as opposed to point slope form. You may need to solve for the slope to deal with working with two lines. I can, right? What does it mean? Two lines to be perpendicular. Well, more than just they cross. They cross in a special way with a 90-degree angle. I usually put a little square in the corner to indicate a perpendicular connection. You'll also see, instead of the word perpendicular, you'll see the word orthogonal. You'll sometimes see the word normal to describe the same idea. Okay, how can I tell from my equations if my two lines are perpendicular? Really close. Not just inverse, reciprocal to one another, but also negative to one another. We usually write it as multiplication. I write that the product of those two slopes has to be -1. I can write M2 as -1 over M1 equivalently. Or, just like I had to have an or up here, what's the or down in this case? What's the exception? If I don't have a slope in here, I'd have a problem, right? What if one of my lines is horizontal? What's the slope of a horizontal line? What happens when I put that in here? I can't divide by 0, right? And it's undefined, so what has an undefined slope? Aha. So frequently, we will ask about a particular line, and rather than give you a slope or give you 2 points, I'll give you the line it's parallel to, or I'll give you the line it's perpendicular to. And I'll say, I want you to find a line perpendicular to this, but now it goes through a different point. I have to find the slope, I have to find a point, then I can build the equation of my line. But I'll be taking the line I was given to build the slope for the new one. Questions? Okay. Linear equation, equation of a line, are also known as first-degree equations, because in the general form, the highest power that appears is 1, x to the first, y to the first. But I can look at all sorts of other equations. If I allow myself to include not just first powers, but second powers, then I'm looking at something called a second-degree equation. The most common thing we will see that is a second-degree equation is a circle. So what's the equation for a circle going to look like? Yeah, I'm going to need a radius, right? But I'm going to need something else. What goes with the radius? Well, the radius and the diameter are just two different ways of measuring how far across my circle is. The radius is from the center to an edge. The diameter is from edge to edge. But I just said a magic word in there. That's for the area of a circle. If I know the radius, the area of a circle is pi r squared. Distance. Distance. If you think of a circle, I've got a center and a radius. And I want all the points where the distance to the center is the same. So let's suppose that my circle has a center, and I'll make up a pair of letters for the moment, H and K, and it's going to have a radius, R. I don't care what these numbers are. They could be anything we want. But let's think about what we would do if I wanted to say a point on my circle is this far away from the center point. We talked about distance yesterday. What's the distance formula? That's our slope formula. Y2 minus Y1 over X2 minus X1. That was the slope in a line, looking for the distance between two things. That's our Pythagoras, right? We took the square root to get the length of the hypotenuse. So I would say that this point and then my other point, right? So I have a point on the circle. And I'd say the distance between these two has to be this. So I'll take X2 minus X1, and I'll square it. And I'll take Y2 minus Y1, and I'll square it. And I'll take the square root of all of that, and I'll set it equal to my distance. I hate equations with square roots in them. With the white hot passion of 1,000 suns, having the square root makes me twitchy. So let's square both sides. This is my default equation for a circle. Instead of just using the distance, I use the square of the distance to get rid of that square root involved there. And this is clearly going to be a second degree equation. If I were to multiply this out, I get an x squared and then an x term and a number. I get a y squared and a y term and a number. Then I have that r squared on the other side. So if I were to multiply something like this out, I might get something that looks like this. I multiply out the x bits, I multiply out the y bits, I put all the numbers together. So whatever number from k squared and h squared and r squared, I kind of group all that garbage together and I get 7 in the end. I claim this is a circle. At this point, most of you are going, sure it is. I believe you. You shouldn't. I can lie my ass off. You shouldn't believe me. How do we know whether or not this is a circle? I only know this is a circle if I can take this equation and turn it into this one. How am I supposed to do that? I promise there's a trick you learned in our algebra class where you did do that. My goal is to rearrange all the terms in here so I have things that will be squared. We even gave this a name. Anybody remember the name of this process? Algebra was a long time ago, man. Understand? We're going to complete the square. So I'm going to rearrange this a little bit. I'm going to put the x pieces together and leave a little space where I would get something from the end of this. I'm going to put the y pieces together, leave a little space. I'm going to move the 7 to the other side. And now I think to myself, this part and this part should be these parts. But there's a gap there. It's incomplete. I need to fill in that blank space with the right number to make this a square. How am I supposed to pull this number out of my ear? Hang on a second. I need a little bit of scratch paper here off to the side. If I have x plus something squared, and I multiply that out, that's x plus h times x plus h. Multiply it out for me. Distribute. What do I get? Jordan? Now, the best part is that x and h are numbers, right? So does it matter whether I do xh or hx? Aha! This number in front of the x term is twice the h I need for the n term. So let's take this number and cut it in half. That's -1, right? What happens when you square -1? That's the number that needs to go on the end to make that a square. Now, I'm not done with my completion yet. I added 1 on the left side. I can't just do that out of nothing. If I add 1 on the left side, I have to add 1 on the right side. So since I added this 1 here, I'm going to add a 1 there. Now do it again. Let's do the same thing with this set of parentheses. So half of -6 is -3. Square that, and you get a 9. So if I add a 9 here, I add a 9 here. Now, best part. X plus h. I know what the h is. This is y, oh, it's minus, right? Y minus k. The only difference is going to be the plus or the minus. This number, take the square root of x squared, you get x. Square root of 1 is a 1. Take this sign and bring it down in the middle. Same thing here. Add all this up. This is a circle. Ta-da! What is the center of my circle? Go compare it to the equation in the box that's up off the top of the page. The radius is on this side. But what's the center of this circle? Aha! 1 and 3. Those are both positive numbers because up here we have x minus h and y minus k. So the minus signs don't count. The center is 1, 3. The radius is? Oh, careful. It's root 3 because this is r squared. Now, I did say that this was the most common second degree equation. But in your pre-calculus class, your trig class, you did a lot of others. Not just circles, but all the other conic sections. Mother. Okay, wait a second. I know for a fact we did these. I just don't like them very much. I don't remember a lot about them, but they're all going to be very similar to our circle idea. What's an ellipse? The internet is your friend. It looks like an oval. So take your circle and imagine stretching it, right? Well, that means that I'm going to change, and it's not going to be the same distance each way, right? If I stretch it horizontally, it'll be longer in the x direction, shorter in the y. If I stretch it vertically, it'll be longer in the y direction, shorter in the x. I don't have one radius anymore. I've got two of them. But that's a pain in the neck, and trying to make this equation look right with two radius numbers just isn't going to cut it. So what we do instead is we divide this equation. An ellipse if I were to write a circle, I'd write equals r squared, yes? So instead of taking equals r squared, I'm going to say I'm going to make this equal to 1. So I divide by the radius, but now there are two different ones. And normally we let A be the bigger one. So if I've done this, then it's bigger in the x direction. If I want it to be bigger in the y direction, I'll switch the two letters. It's not a requirement. I just need to know where the bigger one is. That's the longer direction. That's called the major axis, and thus the major radius. And the other one's called the minor. So an ellipse is stretched. In order to stretch my ellipse, I can think of taking the point at the center and kind of ripping it into two pieces. And it turns out that that's actually the way this works. Instead of measuring the distance to one point, we measure the distance to 2 points. And we add those distances together. So in an ellipse, we no longer have a single center. We have 2 points on either side, which I will call C1 and C2. And those are the focal points. They're called foci. Now, I'm a horrible artist, so please take this picture with a cubic meter of salt. But here's the game. If you pick a point on the ellipse and you measure from that point to each of these foci and add those two distances together, they are the same no matter which point you use. I don't care if you go to that one point, or if you go to a point down here, or if you go to a point over here, or even if you go to A itself. The total distance adds up to be the same. By the way, it turns out to be exactly the same as the distance across the widest part of the ellipse. Originally, these were designed as pieces of a cone. That's why we call them conic sections. You take a cone and you cut it at an angle. The ellipse is cut shallow, not quite horizontal, but not as steep as the side of the cone. And in Greek, the word for under was ellipsos. So we got under the angle, that was an ellipse. The other thing I really like about ellipses is they have a reflecting property. If I stand at the point C1 and I whisper, the sound will bounce off the walls of the ellipse and recollect at point C2. If you stand here and I stand here and I'm talking at normal volume, you will hear me like I'm standing right next to you. The person 5 feet from me might not. They built a building like this in Washington, D.C. It's called the Whispering Gallery, and there are 2 stars on the floor. The entire building is not just shaped like an ellipse horizontally, it's shaped like an ellipse in the design of the roof as well. And if you stand in one star, somebody 80 feet away at the other star will hear you no matter how quiet you are. When they built the room, it was designed for an international conference. They put the Soviet Union at one star and put the CIA at the other. We could listen to them the whole time they were there. The most common use for this idea nowadays is in ultrasound. If you have a kidney stone, I hope you never have a kidney stone. Oh my God, please don't have a kidney stone. It's like getting punched in the back by Mike Tyson. Not going to be a good thing. They will put you in a bathtub shaped like an ellipse and position you so that the stone is at one of the foci. And then they'll put an ultrasound generator at the other one, and they'll send out a pulse of ultrasound. And the pulse will bounce off the wall and bounce back onto the stone and shatter the stone. And you don't have to have surgery. It's called ultrasonic lithotripsy. And that's a lot easier than going under the knife or having them put a camera and a wire up to your kidney and blow up the stone that way. Not a fun time. You had a question. The total distance, the distance from any point to C1 plus the distance from any point to C2 is a constant. And that constant happens to be the diameter of the ellipse, the long one. I don't expect you to have all this stuff memorized. We did talk about it in pre-calc and in trig. I cheated on our Canvas page. There's a handout. There's everything we just did. And there are numbers here. The number A and the number B, and then there's a formula for C. Wait a minute, that's almost the Pythagorean theorem, isn't it? Instead of a plus, it's a minus. And notice the symmetry. If the bigger number's under X, the long direction's the X. So the long is top to bottom, symmetric. If the bigger number's under Y, going this way, that's our major axis. And we can go up or down from our center, left and right from our center, to find the minor axis. Okay. You should download this or look at it on our Canvas page while you're looking at these assignments. There's a lot of places where some of this information will be really, really helpful, but most of it is just going to come in little bits here and there. If I take those 2 points and turn the center into those 2 foci, I can keep spreading them out, right? As I spread them out further and further and further, my ellipse changes shape. That's called the eccentricity. Skinny ellipses versus more round ellipses, they change shape. A hyperbola is what happens if you take an ellipse and turn it inside out. So imagine, instead of having everything go in towards those foci, they go out from those foci. So my shape now changes. For a hyperbola, I'm going to see something like this. Now, this particular hyperbola is going in the x direction. I could just as easily have one that went up and down in the y direction. But what's really interesting to me is that the equation for a hyperbola is almost the same as the equation for an ellipse. The equation for a hyperbola has a minus sign in the middle. That's the only difference in the equation. Instead of adding the two distances, I'm subtracting the two distances. But I'm still measuring the distance from C1 and C2, only down here instead of add, I have minus. By the way, whichever of these two is positive, that's the direction it goes. So I wrote x squared minus y squared. That's why this one goes from left to right. If I did y squared minus x squared, it would go up and down. Again, same set of formulas. In English class, we talk about hyperbole. Hyperbole is over-exaggerated, overwrought speech. Hyperbola means excess. The angle is now bigger. In ellipse, it was smaller than the side of my cone. In hyperbola, it's bigger than the side of my cone. And that's why the shape hits both sides, the top half and bottom half of my cone. There's a lovely illustration in Appendix C of a cone with all of these things drawn on them. And if you go to the Enrichment Center, we actually have a physical one that you can take apart. Okay, wait a minute. Too small angle, too big angle. What am I missing? Goldilocks, just right. Just right is a parabola. And that means you hit the side of the cone and you never come out of that side of the cone. A parabola, instead of having both pieces be square, a parabola only has one square. Huh. Okay, wait a second. I know this one. I've seen this one before. What's the graph of x squared look like? Looks like that. Great. But want it to go down instead? Put a negative in front of it. That one is going to go to the right. If I put a negative in front of the y here, it's going to go to the left. So which term is squared tells me which direction it goes. Frequently, again, I'll put in the k's and the h's. frequently we'll take the number in front and we'll pull a 4 out of it. So in this case, when I have a 1 in front, I would think of that 1 as being 4a, and then a would be a quarter. What does that number mean? Well, that number means the focus of my parabola is that far away from the center. This number a represents that distance. So that's our distance a. From the vertex of our parabola to our focus, F, instead of C. By the way, if you go the other direction, the same distance, there's a line here. It should be parallel to the axis, but I'm a crappy artist, so forgive me. This line is called the directrix. And you go away from the directrix around the focus. Remember our distance comment? We talked about distance to the focus. There's only one focus here. I can't add something, I can't subtract something. I'm going to measure against something. If I pick a point, the distance here and the distance straight down to the directrix should be equal. Those two lines, yeah, this is where I'm a crappy artist, those two lines should have the same length. And that tells me how wide or how narrow my parabola is. Literally, by changing the distance between these two, we're changing the focus of our opening. Okay, who's got an old-fashioned camera that they have to adjust the settings on? Or who's ever adjusted the settings on your iPhone camera? Focal distance and focal length, we're moving that point. Aperture is a function of focal length. Now, again, the equations are here. But I'm going to cheat even harder this time. Grab your calculator. Hit the apps button. Look, right there, apps. Look at number 4. Ready? There are the equations again. Not only are the equations there are the pictures that go with them. I don't have to memorize this crap. They built it into the technology for me. I hit the escape button. I can go look at one of the other ones. Notice they call it P instead of A in this calculator program. I didn't write the textbook. I don't get to call it the same thing in every place. Same idea. Quit. I have it all with me. I don't have to have that formula sheet, but it's useful. Questions? You feed it H and K, A and B, or P, whatever the other numbers are needed, it draws the picture for you. Oop, wrong one. Okay, I've just fed it numbers. A is 4, B is 2, H is 1, K is 1. If I draw a picture of this, what should I see? It's an ellipse, so it'll be an oval. It should be to the right and up. H and K are the center. A is 4, so it should be long, left, right. It should go 4 units left and 4 units right. So if we're at 1, we should go to -3, we should go to 5. B, we should go 2 up and 2 down, 3 and -1. Ta-da. Not only draw a picture, it put the center of the ellipse right in the center of the page and made the box exactly the right size. Ta-da. I think it is useful and beneficial to remember these properties of ellipses, hyperbolas, and parabolas because they come into play when we start to do applications for the trigonometry we are doing, for the calculus we are doing. A lot of the pieces we're going to work with, I'm going to look at, oh, I need a shape. I can use one of these because I know what they look like. A lot of motion and physics and pieces related to calculus use these as well. Questions? If you're looking at me like I've never heard of this crap, you're in the wrong classroom. We need to talk about a switch. But y'all, most of you are looking at me like, okay, I remember this vaguely. That's good. Okay. From trigonometry, well, from circles, I get trig. All of the work that we did in pre-calc involving trig is going to be foundational to some of the things we do a little later on. I am an evil, evil, evil mathematician. Degrees suck. I want to use radians. What's a radian? I'm used to doing angles in degrees. Y'all kept telling me 90 degrees earlier for right angles. I want radians instead. How do I get there from here? I got to figure out which way I'm going, right? So to go from degrees to radians, I multiply by pi over 180. Now, why am I doing that? That's the real question. Why am I using that number to switch back and forth? Aha, 180 degrees is a straight line, right? And if I go across the top of the straight line, that's half a circle. If I go around the other one, that's another half of the circle. And what's the distance around a circle? 2 pi times the radius. What circle did we always use in trig? The blank circle. You made a picture, you drew, what circle did we use? Well, the radius is 1, so the distance around a circle is 2 pi. 180 degrees is half the circle, that's 1 pi. If I want to go the other way, then I'm going to use the 180 over pi, because I'll divide out the radians and I'll multiply by the degrees. Think about the units. This is in radians, this is in degrees, so that's my conversion factor, depending on which way I want to go. If I write degrees here, this will cancel. The best part about this is it doesn't care what the radius is. Degrees cares what the radius is. As my circle gets bigger, 1 degree gets further and further apart, but 1 radian stays exactly the same distance apart, no matter how big or how small that circle is. Radians is actually a measurement of the arc of the circle compared to the radius. It's a measure of arc length. On page A24, in the appendices, you will find what I hope is a familiar table. Come on, turn the page. Of the angles we use the most often in degrees versus radians. Those 5 need to be the ones you have instantly at your fingertips. You know the best part? I mean that literally. Hold your hand out in front of you with your pinky horizontal and your thumb straight up. 0, 90 degrees, right? Hold your fingers comfortably, and it's 30, 45, and 60, isn't it? There they are. Now think of the fractions. This is 1/6 of the circle. That's the smallest one. 1/4 of the circle and 1/3 of the circle. Smallest to biggest. And that is halfway across the top, isn't it? So that's pi over 2, pi over 3, pi over 4, pi over 6. They're right here. I don't ever lose them. I got 2 sets just in case. And right now I still have all 10 of my fingers. That is not true for everybody. So you should get it in your head, not as just on your hand. I did have a student a couple of semesters ago who unfortunately only had 1 hand. And we were in physics part of calculus where I do a bunch of stuff with right hand rule, and she only had her left hand. And I said, I'm terribly sorry. This is going to piss you off all semester long. She was right. It did piss her off, and it worked. Okay. By default, I put an angle in standard position when I go to measure it. Then I'm measuring from the positive part of the x-axis. We often use Greek letters for angles. I will use theta most frequently. It's just whatever you want to call it. You can call it Fred. I don't. This is my angle theta. It's measured in this direction positively. That means that this direction is negative. So counterclockwise is my positive direction. Again, here's where my right hand comes into play. My positive direction going up is this way. And my negative direction going down, it's right-handed. By the way, this is why tightening a screw, you turn to the right. You're moving your thumb forward. And loosening it, you're moving your thumb backwards. By the way, that's a strictly American trick. I found this out the hard way. On a British car, the nuts on the right side are right threaded. The nuts on the left side are left threaded. I didn't know that until I damn near stripped a bolt on my friend's MGB. Because that way they're both turning against the motion of the wheel. And they tighten by the vibration rather than loosen from the vibration. Physics is a wonderful thing. But don't do it when you're an auto mechanic. I broke the damn torque wrench. Okay, but that's my right hand again. I'm going to take these angles, I'm going to apply ratios to them. on this particular angle. I'm going to put a point. I don't know what its coordinates are. It's X and Y. But by definition, X will be this value. And Y will be somewhere over here on the Y-axis, right? That's what those coordinates mean. So I can think of this angle and the point on it as creating a right triangle. Whose sides are X, Y, and R. Hey, wait a minute, why R? There's got to be a reason. The hypotenuse of my triangle is the radius of the circle we're making at that point. Which means that I know R follows the Pythagorean theorem. Now, if I had hit the zoom button on this camera, I can make this triangle as big or as small as I want, right? That doesn't change the angle at all. It does change the lengths of the sides, but it changes them in proportion to each other. So if I divide these sides one by another, I'll make a ratio. And no matter how big or how small that triangle is, that will be the same based on just the angle. These are the primary three trigonometric ratios. Normally, I think of them based on their position relative to that angle. So instead of Y, I will talk about the side of the triangle that is opposite the angle, because it's across from it. And I'll talk about X as being the side adjacent to the triangle. Oh, and then this one was the hypotenuse. So opposite and adjacent refer to the legs, not the hypotenuse. Well, then I can write sine is opposite over hypotenuse. And I write cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. And that is the most common mnemonic in all of trigonometry. So, sine, cosine, and tangent, and which side of the triangle is over. Again, there are some angles we use so often that we should have these memorized. But before I get to the list, I would point out that these are fractions, right? I can flip them over. And if I do that, I rename these ideas. So if I write instead of sine or cosine or tangent, I write cosecant of theta or secant of theta or cotangent of theta. Now, I am personally rather annoyed at this. Sine of theta and cosine of theta, right? And secant and cosecant. But notice that secant goes with cosine and cosecant goes with sine. What? It turns out these are actually named these things because of the way these lines cut a circle. The word secant comes from the Latin secare, meaning to cut. And they cut the circle. The word sine is actually sine because people didn't know how to read Arabic. The first trigonometry books were written in Hindi and Arabic, and they were translated into Latin and Greek in the mid 1400s. And the word for sine was jiva, which means string of a bow. I want you to picture the arc of a circle as a bow. Think of the string of the bow, and then you draw it back to the center of the circle. Hey, wait a minute. A bowstring drawn back. Isn't that the sine from right here? So they called it the bowstring. But Arabic and Hindi are diacritical languages. The way you write them, you don't write vowels. I am absolutely horrible at writing in either of these languages, so I'm not going to. But what happened is the word jiva gets written like this. Now you have to figure out, based on the marks above and below the letter, what vowel goes with it. Modern Hebrew is written in the same fashion. Modern Arabic is still written in this fashion. The person who translated this book didn't read this as jiva, they read it as jaiv. Instead of writing J-I-V-A, they wrote J-A-I-V. And that means fold. A fold in a piece of cloth is a pocket. What's Latin for pocket? The pocket in your face behind your nose is called what? Say it louder. A sinus. Sign for pocket from fold, because we can't read Arabic. These are the stories that stick with me after reading history. Okay. There's a set of angles that I told you should know, right? These angles that you should know have trig functions you should know. Now, I'm going to also tell you that these three, secant and cosecant and cotangent, I don't bother to remember. I use this. But I want to think about just sine and cosine for a minute. I need to memorize those. Those goes with these angles, right? Okay. You want to do sine or cosine first? Okay. Sine, start here. Start with your pinky. Start with your pinky. Count up. 0, 1, 2, 3, 4. Yes? Pick which angle you want to stop at. Tell me what number it is. Take the square root of that number and divide by 2. 0 over 2. Square root of 1 over 2. Square root of 2 over 2. Square root of 3 over 2. What's the square root of 4? 2 over 2 is 1. 0, 1, 2, 3. Square root of 1, square root of 2, square root of 3, square root of 4 over 2. They're right here. You want to do cosine? Don't start from your pinky, start from your thumb. Do the exact same thing. 0, 1, 2, 3, 4. Take the square root, divide by 2. I could spend an hour trying to memorize this table. Or I could remember the trick on how to count to 4 and which one to start from. How do I get that one? Well, this requires me to either memorize this table or to think about the relationships trig functions have with each other. Because you'll notice down here I wrote cosine and secant and cotangent in terms of those, right? Here's my next sneaky thing. Tangent is sine over cosine. So if I know the sine number and I know the cosine number, I can just divide them. I just turned trying to memorize all of this into just knowing those two. And I can get the rest of them from here. I hate memorizing stuff. It makes me crazy. The less I have to try and memorize and regurgitate, the happier I'm going to be. Instead of 6 columns, I have to know 2. But that means I need all these formulas relating trig functions to each other. As a matter of fact, in our trig class, we did a whole lot of these. Trig identities. There were literally dozens of them. Page A27 through A29 has a whole bunch of these. This handout is on our Canvas page, and unfortunately, it's 2 pages long, and I'm going to tell you right now, I don't want you to memorize most of these. You see those 2 marked off with a pencil? Those are the ones I use the most. These 2 right here. Those are the 2 I would recommend if you want to memorize something. Those are the 2 I would memorize. Otherwise, we're just going to use them as we go along. Really, basically, I think these are the things that you should, from your algebra class and trig class, have committed to memory. And those top 2, exponents and logarithms, logs were a painful subject for a lot of people. So I think remembering that exponents and logs undo each other is an important piece of this. And how to change from one base logarithm in ln to log base whatever else, like log base 10. I think those are useful formulas to have. Questions? Yes,
Can you put that over to the complication? Okay.
yeah. Oh, those 2, by the way, they're right here. They're in the same place. But yeah, those are the only 2 I really use often enough to make them worth memorizing. You should look at the answer keys and the homework problems for the appendices. I put them on our Canvas page. That will give you the opportunity to look at the sorts of things I am expecting you to be able to do. Let me jump to our Canvas page for a second. That's not our Canvas page. This is our Canvas page. Boop. Okay. Reference files. There are the conic section files. There's the long version of the trig formula. There's the table that I just showed you. So those top formulas, formula sheets, they're there for you to have for as long as you want them. This stuff down here we'll get to. This using a graphing calculator document was written by one of my teaching assistants when I worked at the University of Pittsburgh in the year 2000, but it's still accurate. And if you have some questions about some of the things on the graphing calculator, please feel free to take a look. This top document, Francis Sue is the former president of the Math Association of America. He's also an author, and he really wants us to think about the way in which we communicate. And communicating in math is foundationally different than communicating in just about any other course. Because you don't get to write sentences the same way. You get to write equations, which kind of sentences. If you are interested, I think it's worthwhile to take a look at that article. The rest of these we'll get to later. Here's the playlist, my Discord server, the Google Meet for office hours, all sorts of other things that we will use. And there's the list of the homework keys. As you turn stuff in, that's where I'll post them. There's the review sheet. If it doesn't have a green light next to it, you can't see it yet. And there at the bottom, that's where all the papers I've been writing get scanned and uploaded for you to have access to subsequently. Tomorrow, we're going to actually start looking at calculus itself using these as a backdrop. So calculus is algebra of motion. Let's start with the ideas of how things move. You should have received an email earlier this morning about inclement weather. I have been told we're getting somewhere between 1 and 1.5 million inches of snow over the weekend. I don't know what's going to happen Monday. But if I have power and I can't get here, I'll teach from my living room. I'll bring this camera home. I'll do exactly this. It'll look just like this. Those were in the instructions. I will send a Zoom link along with an email. We should get information from the institution sometime Sunday. Keep your fingers crossed for reasonable snow. I hate being snowed in. I will see you all tomorrow. Have a wonderful rest of your day.